Yeah, we should.
Yes. Yeah.
I'm waiting for that at the end. Okay. I may have up just this
From these desert southwest. Very far away. Yeah, I resigned. That helps. I have green boots. I didn't test. Everything's better when your feet are dry.
Okay, let's get started. Welcome to today's High Energy Seminar. Our first speaker today is Bart Ripperda. He's currently a postdoc prize fellow at Princeton and the Flatiron Institute in New York City. He's been working on plasma and magnetism for some time, but in different guises. He got his bachelor's in engineering from Eindhoven University of Technology in the Netherlands, and then he got a master's in both engineering and in physics. And he was already working in Magnetohydrodynamics, but for different types of applications. He got a PhD in mathematics from KU Leuven University in Belgium, working on magnetic reconnection and particle acceleration. He was a visiting scholar at Columbia and a Humboldt postdoc prize fellow at the Institute for Theoretical Physics in Frankfurt. In 2018, he became a member also of the Event Horizon Telescope. And since the past year, he's been at Princeton and CCA. So today he's going to be telling us about magnetic reconnection and plasma formation in black hole accretion flows.
Thank you very much for having me here. I'm actually very excited to talk to this big group of astrophysicists and astronomers, because usually I talk to plasma physicists, and this is a much more interesting crowd. It probably means that I have to give you a little bit of an introduction before we get to the interesting stuff. So I'll start with my field of research, which I broadly call relativistic plasma-astrophysics. This means that I look at compact objects like black holes, neutron stars, white dwarfs, and all of these show plasma effects on a whole range of scales. You can think about accretion, about dynamo processes, turbulence, reconnection, jet launching, flares, and all of these effects are more or less guided by general relativity, meaning that we are looking at strong gravity, that we're potentially looking at gravitational wave emission, which I'm not going to touch upon today, and secondly, that these objects are usually highly magnetized, meaning that special relativistic effects can become very important as well, such as highly accelerated particles and even quantum electrodynamics effects like pair creation, radiation, which I will also not talk about today. So what will I actually talk about? As you all might know, I think better than I do, stars and black holes can launch flares from their magnetosphere, from their accretion disk, from corona, from a jet. We actually don't really know where they come from, at least not in all occasions. But here you see an example of a flare from the sun, which is actually our nicest and closest laboratory. And we see that there are magnetic loops here which at some point open up and burst and launch a flare. These flares usually consist of non-thermal emission that we observe, and the non-thermal emission comes from accelerated particles. And we nowadays in plasma physics, we think that these particles accelerate in what astronomers often call hotspots and what we in plasma physics call plasmoids. Those plasmoids, they can form due to magnetic reconnection, and I'll explain later how exactly that works. But the idea is that energy can be transferred from very small scales to large observable scales. That also causes the main difficulty to model all of this, because we want to model the small scale plasma physics event that, due to its interaction with a strong gravitational and electromagnetic field, grows into a macroscopic observable effect. So we need a numerical method or a theoretical model that captures both the small and the large scales. So I will show relatively few equations, but I want to set the scene properly. If we want to model fluids or plasma in strong gravity, we usually say that the plasma is relativistic. This means, first of all, that the magnetization parameter, which shows the magnetic enthalpy density, or the magnetic energy, if you wish, over the thermal energy, thermal enthalpy density, that is usually larger than 1, meaning there is a lot of magnetic energy to be dissipated through, for example, reconnection events or turbulence into particles that emit radiation. Second, it means that your flow or your particles can reach relativistic velocities. And the third part, here in red, if we have strong gravity effects, it means that our space-time is typically curved, or mathematically speaking, we have a non-zero Riemann tensor. To analyze such a problem, you need a set of equations. So first of all, to describe the fluid motion, you need a set of conservation laws. For example, in my case, the inviscid Navier-Stokes equations, or the Euler's equations. And to describe the electromagnetic field dynamics, you need Ampere's equations. Here you see them in covariant form, but they're nothing else than your standard Magnetohydrodynamics equations. If you actually have a zero Riemann tensor and you have velocities much smaller than the speed of light, this set of equations reduces to Newtonian magnetohydrodynamics. There's actually nothing special about it. I solved those equations on a grid because they're highly nonlinear and I'm looking at very chaotic processes, so it's very hard to do something analytically. So quickly browsing through, from the left-hand side we obtain the evolution of the electric and magnetic field. From the right-hand side, we obtain the evolution of the fluid in terms of, say, density and momentum. We couple the two equations in an arbitrary spacetime, say the Kerr spacetime for a spinning black hole. We plug in the electromagnetic fields into the stress energy tensor for the Navier-Stokes equation, and we plug in the fluid as a source for Maxwell's equation. The fluid is a fluid of charged particles. We put all of this on the grid. And I solve this with a black hole accretion code, which is a finite volume MHD code with mesh refinement. I won't go into details on that. I think it's not so interesting. What's important for flares is that they are generally powered by non-ideal processes in the plasma. However, most models in astrophysics, in magnetohydrodynamics, assume that the plasma is ideal. This means that there is zero resistivity, or that the plasma is infinitely conductive. And this is generally a good approximation for accretion disks, for example. According to Alfvén's theorem, it means that the electromagnetic fields are frozen into the fluid, meaning that there can be no magnetic reconnection. Magnetic reconnection is not allowed. And I'll show you later how we can circumvent that in our models. It also means that there is a vanishing electric field in the fluid frame, and that you can describe your electric field in the system as minus V cross B here in current. It's all not very important. It just means, and this I want you to remember, magnetic fields in this model cannot break and reconnect in theory. And second, it is not possible for an electric field to be parallel to the magnetic field. As you can see here, it will always be V cross B, meaning it cannot be parallel to the magnetic field. But it's exactly this parallel electric field that takes care of particle acceleration. So if we stay in this ideal MHD prescription, what can we do? You see here, Crab Nebula X-ray image. I think everyone knows this. We have a pulsar here in the middle. We have a jet, and the jet has a typical kink feature. If we put this in our MHD code, it looks something like this, and you can see that you retrieve global features like the kink and the jet. However, in that kink, you typically expect current sheets to form, so regions of strong current density that can induce reconnection and flaring, and that reconnection and flaring cannot be captured with our model. Just an example. Now I get actually to the application that I'm looking at. We have all seen this image, I think, of the accretion disk of M87 captured by the Event Horizon Telescope. If we make a magnetohydrodynamics model of this, it looks something like this, where macroscopic scales are about 10 to the 8 kilometers. I apologize for the units. I'm a European theoretical physicist, so I talk in kilometers. You have to forgive me for that.
So do we.
Very good. Then we understand each other. And microscopic scales, say typical gyration scale of an electron in a magnetic field, is about 1 kilometer. So you see that there is a huge range of scales involved, and the mean free path of an electron along the magnetic field is typically 10 to the 8 Schwarzschild radii, where Schwarzschild radius is the typical size of the system. The GRMHD treats this plasma as a fluid, meaning that the plasma is not treated as a collisionless plasma, whereas from these numbers we actually see that an electron will hardly ever collide because the mean free path is so long. So all those collisionless effects are actually not properly taken into account in a magnetohydrodynamics model. But it's just these collisionless effects that can cause non-thermal radiation. So this gives us the main uncertainty in interpreting the Event Horizon Telescope results. And you will see this even more strikingly if we look at recent observations of the gravity probe. Here on the right we see, for example, flares of Sagittarius A star, which have been observed in X-ray a long time ago. But last year, gravity actually observed near-infrared emission from a hotspot, and that hotspot was actually moving around, orbiting in the accretion disk. The idea is that magnetic reconnection can form such a hotspot, or as we call it, a plasmoid. It can accelerate electrons to Lorentz factors of, say, 10 to the 6. They emit a lot of non-thermal radiation, and that is what gravity observed. But to describe this whole process, we probably need a deeper model than magnetohydrodynamics. We need kinetic physics. We need to describe this whole process on the particle scale. That's, however, very hard, because as I told you before, the typical gyro radius is 10 to the minus 11 Schwarzschild radii in this system, and this is something you can never capture with a numerical grid if you also want to describe the global scales, which is at least a few orders of Schwarzschild radii. So let's take a step back and let's try to model the process that causes this non-thermal radiation. Let's model it in a box and learn about that. So relativistic magnetic reconnection is caused by anti-parallel magnetic field lines. It's a very simple idea. You have two field lines that are anti-parallel. They form a current sheet because the magnetic field goes through zero. You get a large gradient in the field. That current can dissipate through what we call resistivity or resistance. The field lines can change topology, as you can see here, from being anti-parallel to forming this kind of X point here. And we actually think that in such a system, in the surroundings, everything can be nicely described by magnetohydrodynamics, but inside this little region, exactly where the dissipation takes place, we need at least a resistivity in MHD, or even better, a fully kinetic particle-based theory. Now, how do we do that? We know that the macroscopic aspects are properly described by MHD. We know that we need kinetic physics for small scales. So why don't we try to capture those small scales by a proxy, a resistivity in magnetohydrodynamics that allows the magnetic field lines to reconnect? There's one issue left if you do it like this, and this resistivity is typically very small. We know these plasmas are nearly ideal. They have very high magnetic Reynolds numbers. If such resistivity is very small, it means we still need to resolve very small scales. Maybe not kinetic scales, but still very small scales. So what we do is we do high-resolution simulations, and we use adaptive mesh refinement. I will show you later how that works. Additionally, to ideal MHD, we cannot just solve for the magnetic field, because the electric field becomes dynamically important, and we solve both equations. And we have a source term here on the right-hand side, which mainly depends on the current density. And here you see the exact issue. The current density goes as 1 over the resistivity, meaning that if the resistivity is very small, this becomes a stiff source term, and your system loses its hyperbolicity, meaning that it's very hard to solve. These are all numerical details. I can tell you more about it if you're interested, but I will quickly skip over it. Now the question is, where exactly do these current sheet form in accretion disks? If we want to resolve them, we better know where they form, so that we are not resolving a whole box with extremely high resolution, but actually only the regions that we're interested in. So here's a little comic from Wikipedia, actually, where you see that anti-parallel field lines are pushed in closer together by the plasma, and once they meet in the X point here, they reconnect, and there is an outflow in here in the vertical direction. If we put this in a code like in my resistive GRMHD code, we can actually simulate that, and we expect a whole range of such X points, where in between the X points we get blobs of plasma, which we call plasmoids. So these little blobs here are the ones responsible for the flaring. If you do this in a simulation, it looks something like this. So this is current density. You see indeed that the current sheet here is like pinched. And you indeed see that there is a whole range of blobs. Those blobs, they advect with the flow, they merge, and they can grow into major blobs here. And these kind of major blobs, they're actually energetic enough to power flares. The small ones are not, and are also not observable. So we need this whole process of formation, advection, and like growing into a monster plasmoid on the global scales of the system. Here's a zoom of this whole process. So first you see that the tiny plasmoids form here as the current sheet becomes thinner and tears. They grow and go, as Lorenzo Cironi nicely said. They merge, and actually in between the merger you get like another secondary current sheet where the same process happens. So this is a process that goes on and on. And eventually you have one major thing that is like highly energetic and consists of a lot of high energy particles. So that's not the whole story though. We modeled this nicely in a box, but a real plasma is turbulent, and there's a lot of global dynamics going on. So does such a current sheet also occur in a turbulent flow? If we look at the most standard test for Magnetohydrodynamics code, which is a Orszag-Tang vortex. So you have a vortex that moves around here. This is the mass density. And you see that eventually also current sheet forms here and here, and there are plasmoids here, 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 and here. Looking at current density, you see it even more prominent. And if you zoom in, then you see that you can resolve such a current sheet very nicely, and you can see the whole structure also in a more global setup. And actually, I don't know if it's very well visible, but you see little blocks here, which is my adaptive mesh, my grid. And you see that here, where not so many dynamics are going on, my grid is relatively coarse. But here in the current sheet, where I need a lot of resolution to resolve the formation of those plasmoids, I have a lot of cells. So each little square here consists of 8 by 8 cells. So actually resolve the current sheet with more than 20 cells over the width. Now, what happens if you put resistivity into a global simulation here? If you make the resistivity too large, in my dimensionless code units 10 to the minus 2, but you can think of this as an inverse magnetic Reynolds number. So magnetic Reynolds number of 100 in this case. Nothing happens. The magnetorotational instability is quenched, no turbulence develops, and accretion doesn't really happen ever. So clearly we're wrong, because we don't capture the global ideal MHD physics that we more or less think is correct. If we put the resistivity very small, as we expect it to be, then we actually see that globally it gives exactly the same result is an ideal MHD simulation. You have your black hole here, you have your turbulent accretion flow here, you get a jet out of it. All the global features are there. And here you see this also in diagnostics, for example. This is the mass accretion rate that goes through the horizon, and you see for small resistivities, the blue and the red line and the black line all overlap. And for too high resistivities, the green and the magenta line, the accretion is actually halted. And the same for the magnetic flux through the horizon. It shows the same picture. So we know this resistivity indeed has to be very small. Now, if we put that resistivity so small that we are actually, say, 10 to the minus 14, we cannot resolve it. So that's not an option. If we put it at 10 to the minus 3, we're getting the wrong global physics. So if we put it at this value of 10 to the minus 4, this seems to be a magical value as found out by plasma physicists. This is exactly the magnetic Reynolds, this corresponds to the magnetic Reynolds number, where you get plasmoid formation. So the current sheets can shrink enough to become tearing unstable, pinch a little bit, and form plasmoids. So what I did is I put a resistivity of 5 times 10 to the minus 5, so I put it slightly below the limit just to be sure. In my global accretion disk simulation, I put a lot of resolution, so a resolution of 100 times larger than what you typically do for EHT type simulations, or let's say a factor 10 per direction larger than what you typically do in EHT type simulations. And I see if I can resolve these current sheets and whether we get these kind of plasmoids in the global flow. So here you see a video of what is called a standard and normal evolution, or SANE, as coined by Ramesh Narayan here. On the right you see the inverse plasma beta, which is a measure of current sheets and also a measure of magnetization. We're still in the transient phase here, but at some point you see that you get the semi-stationary or steady-state type of accretion flow, and you actually see all these plasmoid chains here close to the event horizon that do exactly what you expect them to do based on a local box simulation. Additionally, I will actually pause the video for a second. For example, here you see such a plasmoid chain, and if you look at the temperature map, you see that indeed these plasmoids are very high in temperature compared to the rest of the disk. So they're indeed heating up the plasma as we expect them to. And if you go a little bit further, not that far, you see that this happens both along the jet, so these plasmoids can actually escape with the jet, and they're fed by the high magnetization of the jet, and in the disk. So this is, for example, a kind of thing that gravity might have observed, because you see that the plasmoid is ejected in the accretion disk, and it might actually orbit around. Now these are axisymmetric simulations, so I cannot tell you much about the orbit, but they're already challenging enough, and the next step is to do this in 3D and actually see how this thing orbits around. You have another type of typical accretion flow, and it's a magnetically arrested disk, meaning that the accretion is a bit more ordered because there is a lot higher magnetization, which also makes the reconnection a bit more interesting, because if there is a higher magnetization, there is more magnetic energy to actually pump into the reconnection and to get emitted. This process is a bit slower, so to be a little bit patient until it starts. See the same thing here. The plasma falls in, and you get exactly the same thing. So you get a lot of plasmoid chains here. These big current sheets, as you can see, they become plasmoid unstable. But you see that the global flow is much more ordered. There is not so much turbulence. But in both regimes, and we actually think that M87 is in this regime, we see that plasmoids are ubiquitous. They're everywhere. They form along the jet sheet. They can be expelled into the disk, and they can easily orbit. I'll skip this. I wanted to show you my grid, but I think the point is clear. So if you take a nice still slice, you actually see here such a chain which looks exactly like the current sheet in a box that I showed you before. And you get here a monster plasmoid that forms due to the advection and merging of smaller plasmoids. And this is exactly the kind of thing that gravity might have observed, at least that's what they're claiming in their paper. Actually, to make that claim, I would have to do a lot more modeling, seeing what kind of radiation comes from this plasma. But at least such a blob of plasma or a hotspot can form in our simulations, and it can orbit in the disk. And that eventually gives rise to such a flare here. I have one more video for you, and that's a future step, and I want to show you how I model actually what kind of radiation comes from these kind of blobs, because for that we actually need particles. The resistivity is not going to help us doing that. So we put in test particles in our flow, and you can see them here, just a toy simulation here. You can see that these particles actually are trapped in something like a plasmoid here or here, and they move around. So plasmoids trap electrons. Electrons pick up a lot of the magnetic energy and actually stay in the plasmoid while it orbits around the disk or escapes along the jet. I also have a picture of the jet. And those electrons can radiate for that whole orbit, and hopefully that's the radiation we actually see, and we understand where it comes from. Yeah, that was everything, and it's 12:55. So.
Are your simulations three-dimensional?
What I showed you now was an axisymmetric simulation, so two-dimensional. We are working on the 3D simulations.
So how can you be sure that the kind of growing effect isn't just analogous to kind of the two-dimensional inverse cascade process?
Yeah, that's a great question. That's what we have to figure out. So this is slightly different than turbulence, where you have indeed difference between 2D and 3D, because magnetic reconnection happens independently of turbulence. It's purely effect of, say, Maxwell's equations. If we do 3D local box simulations, we see that plasmoids form. They're not single blobs, but they're actually flux tubes. And those kind of flux tubes, if you imagine a blob, like in 3D it becomes a cylinder, right? That's a flux tube. We observe those flux tubes in 3D simulations, just at very low resolution, so we actually don't see this sort of explosive behavior that you see here, where these plasmoids are emitted, but we see that these flux tubes form and then slowly diffuse. But that's probably because our resolution in current 3D simulation is not high enough to capture the full eruption of such a flux tube.
So, yeah, thanks for showing these diagrams mostly on the vertical plane for how these plasmoids seem to be accreting onto the black hole. But gravity found fairly face-on accretion disk, about 20-degree viewing angle. And I'm wondering whether you tracked some of these disks in the azimuthal direction and tried to compare the centroid motion of these disks, and maybe the symmetry might kill some of these centroid motions if they do form symmetrically around the azimuthal direction.
That's exactly what we have to do now, and I totally agree with you. So the question is, well, first, do they form in 3D? And second, do they orbit in the azimuthal direction on the timescales that gravity observes? From local box simulations, we have good hope that that's actually what happens. But in 3D, it is impossible. So these simulations are resolutions of 12,000 by 6,000 cells. In 2D, we can do about 300 cube simulations. So we're an order of magnitude off. We're trying to get to, say, 4,000 cube simulations where we could potentially see this, and then we can track the orbital motion. I could do it in 2D, but personally, I don't think it's very convincing to talk about azimuthal flow in a 2D simulation.
So what is the distribution of the energies in this plasmoid? So you have small ones and the big ones.
Mm-hmm.
So what is the energy scale of those?
So all the energy piles up in the big ones eventually. All the small ones actually, they grow due to mergers. Their energy is confined within, let's say this is a magnetic loop, sort of. The energy is confined, and they go into the big ones. And those big ones are the ones that get enough energy to radiate. At what kind of, let's say, frequency they radiate, what kind of energy they get?
I was just concerned about the total energy in this. So if you say it's big, I mean,
Right.
is it like multiplications of those
Yeah,
small
so
ones?
imagine, so all this energy comes from your magnetic energy density. So in these plasmas, which are highly relativistic, as I showed on the first slide, it means that your magnetic energy density over your thermal energy density before reconnection is very large. So there is a lot of magnetic energy to reconnect and get into these plasmoids. So typically in the jet region here, so let's say in the jet funnel here, the magnetization is tens or hundreds times larger than thermal. So all of that energy can in principle be fed to the plasmoids. So there can be a factor of 10 to 100 of energy transfer. Yeah.
Last question.
What sets the scale for these monster plasmoids? What keeps them from growing even bigger?
Nothing. That's what we're trying to figure out. I think it's all about the time scale. So what we're trying to figure out is if we could get macroscopic ones, say on the size of the event horizon, whether they can grow bigger than this. I think you would need a sheet, a current sheet that exists long enough for more and more plasmoids to feed into this thing. But on an ohmic time scale, which is usually much longer than an alphanic or orbital time scale, this thing would be pinched off. But in fast reconnection, plasmoid reconnection, this all happens much faster actually. So the question is, when is this thing released from the current sheet, because then it cannot be fed anymore. What that time scale is, I don't dare saying, so I can also not tell you how big they would grow, but we're planning to do, like, let's say, what they call plasmoid statistics to look at time and size of the plasmoids. Yeah.
I think we have to move on. But you're around for a little bit, right?
I'm around both today and tomorrow, and actually tomorrow I'm giving the ITC luncheon where I will talk about similar things. So it might be boring.
So if you have more questions, you can find them in the next couple just get off. Our next speaker today is Andra Stroe. She's a Clay Fellow here at CFA since 2018. She works on a multi-wavelength studies of galaxies, AGN, and galaxy clusters with a focus typically on the radio and optical. She's interested in interactions between the cluster environments, the ICM, and the AGN, and also in very high redshift clusters and protoclusters. Andra got her bachelor's degree in physics and earth and space science from Jacobs University in Germany. She got her master's in astronomy from the University of Cambridge, and then her PhD from Leiden Observatory. She was then an ESO fellow at Garching before coming here. So today she's going to be telling us about when galaxy clusters collide, shocking tales of structure formation.
Thank you so much for the great introduction. I hope everyone can hear me. Okay, wonderful. So after the excellent previous talk, I will also tell you about particle acceleration, but on very different scales, on the scales of galaxy clusters. So now we're talking about megaparsecs. And to start off, I would like to kind of give you my view of how clusters form and to try to move away from this idea of trying to compare a field environment to a cluster environment, but to actually look at the cluster and its history and understand how many different interactions need to happen. You need to have collapse of filaments. There's accretion of matter that happens on clusters, and there's also a lot of mergers. And today I will focus on galaxy cluster mergers, which is one of the main ways in which clusters grow. So we all know that structure formation is a very violent process, and I like to highlight that these cluster mergers are actually the most energetic events since the Big Bang, and a huge amount of energy is being released in the intercluster medium when you have two of these massive balls of 10 to the 14, 10 to the 15 solar masses colliding with each other, and this is just showing you a little simulation about two of these subclusters colliding with each other, and the processes that happen and are important is, of course, as you have the two clusters colliding with each other, you have a lot of energy that's being released in the form of bulk motion in the intercluster medium, and then as time passes, you form turbulence in the intercluster medium, and also these massive shock waves that travel through the ICM as well. And this is a slide that I stole from John Zuhon, and he actually used this in an outreach talk, but I think it's an excellent illustration of what happens when you have one of these massive mergers. Of course, on one side you have the bullet cluster, one of very very, very famous merging clusters, and then on the other side you have just a bullet traveling through water. And you can see how here ahead of the bullet, or the smaller subcluster, you form this beautiful shock wave, and also in the backflow you develop a lot of turbulence. And this brings me to the topic of radio, and why we want to use radio in particular in combination with X-rays. This is showing you the example of Abell 2256, and this is a cluster that's undergoing a massive merger, and you see there's a lot of white contours that I'm showing you, and this is all radio emission in this cluster, is completely filling the intercluster medium. And particularly today I would like to focus on these objects to the north that we call radio relics, and they're truly kind of diffuse sources of synchrotron. They're megaparsec sized, so they're really huge. They're as big as the cluster. We kind of exclusively find them at the outskirts of these massive merging clusters, and they don't necessarily have an optical counterpart, so we don't believe that they're always associated with a particular galaxy in the cluster, for example. They're also strongly polarized, so this tells us that they trace relativistic particles and magnetic fields in the intercluster medium. And I think the consensus in the field is that they are tracing massive cluster shocks. So, these objects are clearly interesting. Looking at mergers, about 50% of clusters are undergoing mergers, so they're a very important population. But I'd like to give you my take, particularly from the side of particle acceleration, why they're very, very interesting. Particularly these shock waves that we find in galaxy clusters are relatively low Mach numbers. So we're talking about Mach numbers of 2 or 3 or 4. So they're very different from, for example, supernova remnant shocks, although the physics might be very similar. They're also a wonderful way of studying magnetic fields and relativistic particles in the intercluster medium. And the questions that we're trying to answer is, where are all of these particles coming from? How are they being injected? How are they being accelerated? How do they lose energy? And how do we get so much radio emission in the intercluster medium? And particularly, there's a couple of models that are trying to explain how you can have a shock going through a population of electrons and inject them, accelerate them to relativistic speed, so that they can then, in turn, in the presence of magnetic field, produce radio emission. And some of these models assume a single population of electrons, and then you have a shock going through them, so they're all being kind of accelerated at once. Some of them invoke kind of a continuous injection, and this continuous injection of electrons might be something that happens, for example, in radio galaxies. But in the context of clusters, we believe that you just have a single shock wave that is going through this population of electrons that's sitting in the intercluster medium. And different models, including the Kardashev-Paholchik and the Jaffe-Parola model, have different treatments of particularly how these electrons are interacting with the magnetic field, particularly the pitch angle. Is it isotropized? Is it not isotropized over time? And also you can make different assumptions about the magnetic field, whether the magnetic field is uniform throughout these sources, or whether it's, its strength varies, if it's turbulent or if it's very well aligned. And particularly powerful are radio observations, because different models predict different types of spectra in the radio. So this is just showing you log flux versus log frequency in whatever units. And these different models that I described to you have different predictions, particularly at high radio frequencies, about how the radio spectrum of these radio relics should look like. And particularly interesting is also to look at time scales. So if you're just looking at a single patch of, or let's say a single group of electrons that have just been accelerated, its spectrum is going to be just a power law, very simple. But as time passes and these electrons lose energy, so if you wait, 100 million years, this spectrum will start to be steeper and steeper and more curved. So in a way, if you have a lot of radio observations tracing different parts of these sources, you can say something about timescales and about the time evolution of the electron population. I'm presenting to you a lot of kind of cool physics that we could, in principle, constrain with these radio relics and with these shocks. But think about these mergers, they're very, very complicated. So in order to actually have a good understanding about what is happening, you want pretty simple systems. So, maybe you want one of these massive mergers coming from two subclusters of almost equal mass. Ideally, you would want them in the plane of the sky, so you can really understand the history of the merger, and you can really see the location of these beautiful radio arcs. And these in turn would then give you all of the information you need to be able to constrain the physics. The complication that we have is that to get a very good handle on the spectra of these radio relics, you want kind of an impossible combination of resolution in your radio observations, but also you want a lot of different frequencies to cover. So you ideally would want to cover, 2 or 3 orders of magnitude in frequency to really be able to trace the spectrum across. And particularly important to highlight is that these objects, as I mentioned, they're very large on the sky. So they're, 10, 20 arc minutes on the sky. So particularly for the instruments that we have, this is very challenging as your radio telescope, because it's an interferometer, kind of just doesn't see all of this large scale emission. So we do have some observational constraints, and also you want your clusters to be pretty simple to understand their history. But, we're very motivated, so we put in a lot of observational effort to understand these objects. And particularly today, I will focus on these two objects, the sausage and the toothbrush galaxy clusters. These are massive galaxy clusters at about redshift of 0.2. They're 10 to the 15, 2 times 10 to the 15 solar masses. And you can see here in the background the X-ray emission of the cluster in the grayscale. So you can see that they're clearly elongated in the north-south direction. So we believe from all of the multi-wavelength observations we have and from the modeling that we have done in the simulations that these objects are coming from a massive merger happening in the plane of the sky of, between subclusters of almost equal mass. And as the two subclusters pass through each other, you form these wonderful shock waves that are traveling outwards at very high speed and then accelerate particles in the intercluster medium, which then, in the presence of magnetic field, produce these diffuse radio sources, particularly these ones towards the north that, garnered the name sausage and toothbrush, we believe are these sort of relics that are tracing the shock waves caused by the cluster merger. And as I mentioned, we gathered a lot of different radio observations. Here I'm showing you a combination of 7 different radio frequencies. And what I'm encoding in the color is just the slope of the radio spectrum. So this is covering the range between about 150 megahertz to 2 gigahertz. And what you can see that the slope of the spectrum in the radio, as you're going from the north side of this relic towards the south, is getting steeper and steeper. So this is telling us something. These particles that are towards the north of this relic are being accelerated right now, whereas maybe the ones in the south, the spectrum is already steeper, so maybe these electrons have been accelerated sometime in the past. So this tells us something. This source, this shock wave, is most likely moving northwards, and it's currently located at the north edge of this radio relic. Now, we believe that these, what we call spectral index or spectral slope trends, have something to do with, the detailed physics of the source and the way that, the shock is moving, and that we are actually seeing aging of electrons losing energy. However, there were some simulations when we were doing this work that were not prescribing any aging of electrons. They just had kind of an unrelated structure. They had unrelated structures of different shocks with different Mach numbers, and what the simulation was showing in Skillman was that you can have these different shock structures and projected in different ways. They can look almost like you have these spectral slope trends, but the argument here was that it's actually just a projection of different shock structures with different Mach numbers that could give you these different slope gradients. So we were very interested to see whether what we are seeing is actual aging of electrons, or electrons losing energy, or whether we're just a collection of different shock structures that are otherwise unrelated. So what we did was we put all of this data that we had together, and for every pixel in this image, we actually fitted all of these models that I was telling you about earlier, these Jaffe-Parola and Kardashev-Paholchik models. And what these models give you out is actually, you can get directly a handle on the Mach number of the shock at every point, but also it tells you something about the age of the electron, so how much time has passed since these electrons were shock accelerated. And you can see this is an incredibly uniform trend going from 0 age all the way to 60 million years. So this tells us this entire shock wave has a Mach number on average of about 3, and it's clearly moving northwards at a speed of about 2,500 kilometers per second. And because we know that the shock has been produced as these two subclusters merge with each other, we can put very tight constraints on the time-sense core passage as well. So the two subclusters merged about 800 million years ago. What is very interesting to me is that imagine this source is about 1.4 megaparsec, and it's also about 1.5 megaparsec away from the cluster core, but it's incredibly uniform in terms of age. So it's kind of surprising that you could have this shock wave that is traveling through the intercluster medium, and it's still kind of a coherent sheet of, kind of very uniform age across. So this tells us that the inhomogeneities in the intercluster medium are probably very small, surprisingly small. And for the first time, we were actually able to, with our radio modeling, recover a Mach number that also actually agrees with the constraints that we get from the X-ray. So it's really cool when we put the data together that we're getting something consistent. So it seems like we have a consistent picture now. You have these cluster mergers, they produce shock waves, they accelerate these thermal electrons that are located in the intercluster medium in an order magnetic field, and then you get the synchrotron emission over megaparsec scales. However, we're making a lot of simplifying assumptions. As I mentioned, maybe these particles that are being injected are not necessarily thermal. Maybe they've been pre-accelerated by some AGN activity in the intercluster medium. And we're also making assumptions that these shocks are kind of very simple, linear, and that we're having a constant order magnetic field, and that we're also injecting particles at a constant rate. So as you can see, we're talking about spherical Clausian vacuum here, and models that have been around since the 1970s that were basically developed for supernova remnants. And maybe, our understanding, at least in clusters, is not complete. And my argument for you today is that, particularly, let's say pre-2015, we've been doing a lot of observations in the radio in a very narrow spectral range. And when you have 2 or 3 different frequencies, you can fit a power law, you can fit a curved line, you can do whatever you want. You can't really constrain the models. So we really need to push our observations at the very high frequencies and the low frequencies to have more constraining power over these models. And this is exactly what we did. Particularly at low frequency, I would like to highlight how much we've been progressing since, my PhD times. On one side, you can see my very old, circa, was it like 2012, image of this sausage cluster coming from LOFAR at 60 megahertz, and you can see it looks terrible. And this is not necessarily a problem with the telescope as much as it is a problem with calibration and the huge amount of data that we need to process to get a good image out of it. Also, this source happens to be about 6 degrees away from Cassiopeia A, which is pain because it is so bright, and even though it's far away, the field of view is so large in LOFAR that you always kind of see it in there, so that's been really causing trouble. But Dui Huang has improved so much on these observations, and you can see now this beautiful, beautiful image that's factors better in terms of resolution and also sensitivity compared to our best images before. And you can see how the radio emission is really filling the entire area of the cluster. And particularly low frequencies have enabled us to make a lot of progress in not only kind of following up sources that we know, but also kind of unveiling to us new types of sources that we would never see at higher frequency because, for example, they have very, very steep spectra. And this is just showing you a couple of them, including these diffuse sources associated with clusters that are extremely far away from the cluster core. And we honestly really don't know how these objects are formed, and this is why we're going to follow them up with extra observations and with other radio observations as well. So it's really kind of opening up a new field really of study. But particularly today, I want to focus actually on the high frequencies. As I mentioned, these high frequencies give us the opportunity to differentiate between different models. But the question you might ask me is, okay, if they're so powerful, then why haven't we really used them before? And particularly, it's because these radio relics are very, very steep at high frequency, so that means they're very faint. And also the field of view of radio telescopes at high frequency is super small, which means you have to do a lot of mosaicing, and it's just very, very challenging observationally. But we said, you know what, let's just try. Before looking at these objects with instruments such as KARMA or AMI, for example, the highest frequency detections that we had were about at 5 gigahertz. And we said, okay, let's go and try to see if we can detect something at 16 gigahertz. And we actually, with 2 separate interferometers, we detected the radio relic quite strongly. So this is the synchrotron emission from these sources, despite us kind of expecting to maybe see some Suniev-Zeldovich effect there. It's mostly just synchrotron emission from the relics themselves. And then we kind of got a little too confident, and we said, okay, if we can do 16 gigahertz, let's try to do 30 gigahertz with KARMA. And of course, while we were getting these beautiful detections at 30 gigahertz, KARMA got decommissioned. I am a very unlucky person, I'm going to tell you that. But still, this kind of pushed a new impetus in the community to try to look at these objects at high frequency, and particularly single dish observations are very powerful. However, you can see the resolution is pretty bad at these 6 to 10 gigahertz frequencies. So we're making strides, but it's still very difficult with single dish instruments because the resolution is very limited. Now, as I mentioned, we now have coverage from 150 megahertz all the way to 30 gigahertz. This is giving us a huge baseline to look at the spectra of these sources. And I mentioned these 2 relics in the north of the sausage cluster and the north of the toothbrush cluster. And we put together this spectrum of these sources. It's an integrated spectrum when you sum up all of the emission. And you can see there's a clear trend of steepening towards high frequencies. And this wasn't necessarily expected in this very simple model where you just have a single shock and is going through the thermal electron population in the intercluster medium. Then you would expect just a single power law. However, we do see this steepening at not at high resolution, at high frequency. And there could be a couple of things that are causing this. As I mentioned, particularly at 16 or 30 gigahertz, you might have some contribution from the Suniev-Zeldovich decrement because of the interaction of the intercluster medium with the CMB. However, these relics are very far away from the cluster core, so the effect is relatively small, and it might contribute a little bit, but it's not going to bring you kind of a factor of 2 lower. And a lot of other models have been developed trying to explain this. Some people are saying, okay, you might have some turbulent reacceleration in the backflow of these shocks, or looking at pre-accelerated electron populations where maybe you have an AGN that was active and then you get a bubble that just kind of sits there in the intercluster medium. You don't see it. It's very old. It's been there for 500 million years. And then you just have this shock going through and reaccelerating these electrons. And this could also give you one of these kind of curved steep spectra. And also another model would be that the magnetic field is not kind of constant, but it actually evolves with time or with position within the relic. And the idea would be that behind the brightness peak, the magnetic field declines exponentially alongside adiabatic expansion of the gas. And this model reproduces pretty well the shape of the spectrum that we're seeing. However, we have all these different models, and the question is, how can we really discriminate between them as we're trying to, we can fiddle with the magnetic field, we can fiddle with the electron population. You could basically just turn all of these knobs and make your model really fit whatever observations you have. But the interesting thing is that particularly these magnetic field model predictions have then in turn predictions that we can constrain, looking at, for example, the surface brightness. So as you're going across the source from the upstream to the downstream of the shock wave, you should see different behavior of the surface brightness depending on the magnetic field model. However, in order to test this model, we are very limited. We can't do it with current data because at 30 or 16 gigahertz, our source is effectively unresolved, so we don't have any resolution along the downstream direction of the relic. So ideally, we would want much better resolution that kind of matches our GMRT observations at 610 megahertz. So, 3 arc seconds, where we could actually resolve this source beautifully and actually see what the behavior with distance is. And we actually got observations with the VLA. These are kind of very, let's say, exploratory observations. We haven't really tried to do this before with the VLA and XKU and K-band. These are observations between 8 and 26 gigahertz. And the resolution we will be getting, particularly in K, will be excellent. It will be 3 arc seconds. But the problem is, of course, the field of view is going to be very small because this is the VLA, and in these frequencies is going to be very small. So we can't even begin to hope to cover the entire relic because that will take, the age of the universe. But we can do a single pointing, and the idea would be that as long as we only care about kind of surface brightness trends and taking advantage of the incredible uniformity of this source, that we will be able to constrain these models just with one single pointing. And this data has been sitting on my hard disk for a year. Hopefully at some point I will get to it. It's a lot of data to reduce, so it's a big challenge. But in the future, I think the observations that we will be able to get will really make our life much easier, and we won't need to do separate observations with different telescopes in a very cumbersome way, particularly as hopefully the SKA will come up in the next 10, 20 years. It will give us coverage up to 14 gigahertz from the low frequency. So this will give us an entire spectrum for many, many sources very quickly. And I'm also particularly excited about ALMA. It's low band, so what is low frequency for ALMA is high frequency for me at 30 gigahertz. This will also help us, particularly with our sources in the south, to constrain the spectrum at high frequencies. But we also need more realistic models. As I was mentioning, a lot of these models that we're using are very simple models from the 70s or 80s that were developed for supernova remnants. But now that we do have all of these different observations, we have more constraining power, so the models need to catch up with the observations as well. And while this, I would just tell you that galaxy cluster mergers are very violent processes, and a lot of energy is being released in the intercluster medium. You have shock waves and a lot of particle acceleration that is happening. But as we're getting more data, we also need more modeling to understand exactly how they're formed. Thank you, and if you have any questions, please.
Questions for Andra?
No worries. I just give very good comprehensive talks, and then there's no question.
All right. So your first 1970 type model, you had 3 of them, 3 different models. They all predicted turnovers at high frequency. Why did you need anything more complicated? Which one of those works best?
From my particular modeling, I think the JP, the Jaffe-Parola works the best. But this just works for one single source very well. When you're actually looking at more complicated sources where you have a lot of projection, for example, this doesn't fit so well anymore. And particularly, let me put it this way, the Jaffe-Parola is still telling you what happens, okay, if you have a single population of electrons and you accelerate them. But kind of on a more overview way of looking at things, particularly, this side of the source, is it the same, do you have the same magnetic field strength as this part of the source? That is more difficult. Like the Jaffe-Parola doesn't tell you anything about that. So once you look at the source in its entirety, it's much more difficult to use a single Jaffe-Parola model, for example, to describe it. So you actually need a superposition, and depending on kind of how many electrons you have on one side or the other side, the summation of the models it can give you different predictions.
When you were talking about these large-scale structures in the radio, one thing you said is that since they're so linear and homogeneous, that puts a limit on the amount of clumpiness of the medium there. Is that limit consistent with the simulations of the universe, or
as far as I know, I think, at least from studies of nearby clusters, I think you do expect to have more clumps. So we don't really truly understand. It might be that we have a bias in the radio, that you're just tracing a particular part of the intercluster medium. We do not have like not the resolution, but the sensitivity to do X-ray studies of the sort that have been done in the local universe to really be able to, detect clumps or anything like that. But yeah, it is, I think, still maybe some of the simulators in the room, John could maybe correct me if I'm wrong, but I think we're still pretty much surprised as to why you could, you have this sheet and it's just still so uniform and very well behaved. But this is one example. Not all relics are this well behaved, but of course then you have all sorts of observational issues in trying to interpret what is happening.
Is this something that links could help with?
Yes, obviously we need links and we need the SK. I mean, this is for sure. Yeah. I think, particularly looking at cluster outskirts, we are limited by our X-ray observations because, if you're 1.5 megaparsecs away from the cluster core, you can imagine that you need, at least 500 kiloseconds or even more to be able to detect something. So to actually have a true measurement of, shocks at these cluster-centric radii, we definitely need the new generation of telescopes, and I'm all on board with Lynx and Athena.
You've shown this picture, you've shown a plot of a spectrum that declined at high frequencies, like the one of the last plots.
Yep.
And you also shown the Karma image,
Yep.
like a couple of slides before.
1 second, I can get there.
Yeah,
So this is the spectrum, and
no, this one.
this is yes.
Yeah.
This.
So this looks like kind of low signal to noise
Yes.
to me. So aren't you afraid that you're just missing on a part of the source because of the low surface brightness? So not because of Sunyatis and Doge.
Yes. That's fair point. So I have like 4 backup slides exactly discussing this, but I don't necessarily need to go through all of them too. So the idea is that we actually threw away a lot of our low frequency data. So you use a lot of, so for example, we use uniform weighting. We cut in kilo lambda the inner part of the UV coverage that we do have at low frequency. So there were all of our different observations are sensitive to the same scales on the sky. And we are, in terms of spatial scales, we should be covering spatial scales about the size of 3/4 the size of this source. And we also did a lot of simulations to see whether we have a very low signal to noise source, how much flux we might be missing just because it's so low signal to noise. And we are fairly confident that this is not going to explain, it's an effect, but it's an effect at the 10 to 20% level. It's not going to bring us all the way back a factor of 2 where we need to be. And this was actually, to be fully honest, this was also found with single dish instruments that don't have this issue of, losing flux or things like that.
Alrighty, that's time. So let's thank Andra.
Thank you.
What do you think about that?
Oh yeah, you think I looked like 10 minutes after they sent out an email and it was already completely full.
Totally impossible.
Oh, I would love to. I just have another meeting.
Yeah, but I was working on
You said 11.
I mean, not even the accretion time scale, it was just about the jet maybe for like a few hundred parsecs, which of course for Sagittarius A star would be like 0.1 parsec. That's the best that's in the days, and for babies they can go like 1 parsec, but that's quite a lot of so that's still like at least 3-4 orders of magnitude.
But I'm just wondering, like, what scales are important for me about the problem? Like, do we need?
I mean, what we need to do is using machine learning models to get the small scale, more complex for the small scale, what having a self-consistent simulation from the event horizon up to 8 kilowatts that you totally possible.